And okay, good morning, everyone. So today we have another distinguished guest with us, Orhan Fırat, who is a research scientist at Google Research working on sequence modeling and multitask learning with applications to machine translation. So he has made many important contributions to the fields, and he's in fact one of the pioneers on multilingual neural machine translation. And today he will talk about their efforts to push the limits of multilingual neural machine translation at Google. So the stage is yours, Orhan.
Thank you for the great introduction. Thanks a lot for the warm words. And warm welcome, and sorry about the initial hiccup at the beginning. Hi, everyone. So this is Orhan. So I'll be talking about a project that we've been pursuing over the last 3 years. So the project has a name that we call M4, Massively Multilingual and Massive MT. So it sounds like it may sound like a machine translation project, but it's not really a core machine translation project. So you'll notice it's sometimes a systems problem, sometimes a theoretical machine learning problem, sometimes an optimization challenge, and once in a while it becomes a natural language processing problem. So the team was over the years, the team grew quite a bit. So we started the project with only 3 people. But over the years, it grew quite a bit. Now we're almost over 30 people from many teams at Google, Google platforms, Brain, NLP or NLX. Several other teams actually participated. So I'm really happy to be part of the team and happy to share the progress with you. Right, but let's zoom out a bit first. So what happened over the last couple of years, because this is, I'm going to be grounding the project. So the pillars of the projects are actually lying here. So in 2010, around 2010-ish, so we were seeing huge applications and research on embedding-based models, like word embeddings or continuous space representations of words. That was abundant. So that was followed by recurrence, RNNs, recurrent neural networks, LSTMs, GRUs. They were quite abundant. They were almost everywhere. And I actually entered the field somewhere in between these two. And if you were not using LSTM or if you were not using RNNs back then, it wasn't very cool. And it was followed by attention. Attention was introduced in 2014 in an NLP domain. And it literally washed the entire field. And again, that was the cool thing to do. And it was actually working quite well. So that was also the time the sequence-to-sequence models with attention was on par with the state-of-the-art models of statistical machine translation. So it quickly washed the field, and then it was followed by the transfer era. What I mean by transfer era, you pre-train something big, and then you use that pre-trained model and then use it to fine-tune on the downstream task that you have. So there comes the importance of reusable features. Actually, this was introduced early in deep learning in 2006 that you pre-train and fine-tune, but NLP domain discovered this that around 2018. So this allowed the domain to solve many more tasks, and a few examples comes to mind are BERT, T5, GPT-1, 2, XLMR in the multilingual world, and so on. But over the last few years, like 2 or 3 years, we're also seeing a new trend. So that I called here the scale. So what we're seeing here is the first time, at least to my experience, the more compute and data is it yields predictable gains. It's interestingly the first time in machine learning community that you throw more compute at a problem, it's giving you better quality or better generalization. We also seeing once scaled, these models are also doing quite good at meta learning. So in the past, we were using quite complicated methods for meta learning, but as we scale these models more up and up, we are seeing meta learning is becoming quite easy to do. And a lot of new capabilities appear discontinuously. For example, a model that was not doing a task at the half scale is start doing a task once you scale it twice. And a few examples on this realm is GPT-3 and 4, which I'm going to be talking about, and also Turing NLG. So at the end, the project that I'm going to be talking about is that we call M4 is built on these two pillars. So transfer and scale. Let me motivate what was our goal. So achieving universality, that was also in the title. But universality is a bit of a, say, romantic goal. So how are we going to quantify universality? So if you look from the NLP domain, so it was actually not only NLP, it was also the roots of AI. The Warren Weaver coined the term of universality for languages or undiscovered universal language. He called this interlingua. And since 2015, everyone is trying to decipher or to discover this universal language. And if you want to be romantic, I think this is the romantic goal of the project, but there's actually a research question behind that. The question that we're trying to answer at the end is, can we parameterize and learn a communication medium that is generic? So this communication medium could be called interlingua. But we're going to be learning this communication medium using the connectionist paradigm, meaning neural networks. But at the end, we want this communication medium, the learned communication medium, and the parameterization to generalize. So that here the keyword is generalization. But how am I going to do it? Let's first take a step back and revisit what do we mean by generalization. Like simply put, generalization relates the performance of a model on seen examples to its performance on unseen examples, right? So, but what do we mean by seen examples, and what are the inductive biases that we can inject into the model to a model to improve its generalization for the unseen ones? So there are a few inductive biases. I actually introduced these inductive biases. The first one was transfer. The second one was scaling. But where do they come from? Why do we want to, like, how are we going to ensure the model is going to be transferring across different languages, domains, etc.? So there, like, first thing first, there is no machine learning without inductive biases. So you have to introduce these. Even neural nets, they have their own inductive biases, right? And for the case of machine translation, our inductive bias is to improve generalization. Where so what we want to do is first we want to enrich what is seen by the model. So we are basically showing the model during training different views of the world. So we're not only like fixating on single view, but multiple views are shown. And how is this instantiated? In NLP, you can show either multiple domains or you can show multiple languages. So these constitute as the different views of the world. And in practice, you show the model more and more data coming from different domains, different languages, different sources. The second inductive bias is increasing the parameterization. So the neural networks, they're basically nonlinear feature extractors. So, and then they're assumed to be increasing the expressivity of the model and then enriching the parameterization. While doing this, while enriching the parameterization, we're also aiming at making the models more sample efficient. So I'll be like using a single example, improving the loss more compared to the other models. So that's what I mean by being sample efficient. And how are we going to test the performance on unseen examples? How are we going to measure the generalization? These are the topics related to the inference time. I'm talking about the right-hand side here. And for the machine translation specifically, what we look at is the performance on unseen languages. So I trained my model on hundreds of languages. How is it going to be performing on an unseen language? This is the exact same formulation of generalization. Test the performance on unseen examples, but in this case, it's the unseen languages. Also, the languages are, there's a huge debate. What is the difference? Where does the language end? Where does the dialect start? Or what is the difference between a domain, style, or register? So we want our models to be generalizing across all these different dimensions. So it's not only about a language, we also want the model to generalize to different dialects, domains, styles, etc. And in NLP in general, these are handled by control generation at the inference time. As I mentioned, since there are uncountable number of new styles, domains, or registers, so we want our models to be generalizing beyond the countable number of tasks or languages. Of course, another ask is the temporal generalization. For example, we noticed our models were particularly fragile for COVID domain because the vocabulary domain they were all introduced quite rapidly, and our models were surprised by the vocabulary and the style. So we also want the temporal generalization from our models. At the end, our goal is what we mean by universality. We tie it to the generalization, and we want a single model that can generalize across 1,000 languages or more, and also domains, dialects, registers, and styles. So this is pretty much the entire goal of the project. And as a spoiler, no, we have not reached there yet, but I'll be sharing the progress so far. If you're not familiar with machine translation, I'll be giving a brief landscape of like what is the current state of things. So this is let's start with the data. This is the data distribution over language pairs. On the x-axis, you're seeing the languages sorted with respect to the amount of training examples. On the left, you're seeing high resource languages that you have billions of training examples. I want to highlight billions. So this data is basically coming from the web. So it's almost the entire web. And we have billions of examples for high resource languages. These are the languages like Spanish, French, German that dominate at the web. But on the right-hand side, we have low resource languages that are Yoruba, Sindhi, Hawaiian, and we only have a handful of data. So you have like 10,000, 20,000 examples. And as expected, if you throw a strong model or capable or expressive model on this data, on the left-hand side, you're going to be seeing, okay, we're approaching the human quality. We're almost at the parity. So the quality of the systems on this left-hand side is quite good, but the quality on the right-hand side is not really that good. But of course, the x-axis here is spanning only 100 languages. So that's not all the languages and it. So here I just sketched the first 400 languages. So things were good at the high resource end. So it was getting darker as we reached to the low resource end. But if we go beyond the 100 languages, so we are in the territory of unsupervised realm. Because we don't read the availability of parallel data or supervised data is quite limited. So the things get more and more grim in this territory because you only have monolingual data. The learning becomes a lot harder. We always have this assumption of, okay, unlabeled data is abundant, but it's not really the case for the many languages that are at the tail. So how am I going to learn in this data distribution that I have high resource languages, that I have supervised data that is rich on the left, and I have monolingual data that's noisy and I don't have much on the right. So it's like a little bit of an outlier case, but it's a quite challenging problem learning under these constraints. So how are we going to do? Of course, we're going to use inductive biases. In order to, so we're basically using two inductive biases. The first one I mentioned, the transfer. So this notion is known as the positive language transfer for the middle and low resource languages. What do I mean by positive language transfer? Here I collapse the baseline scores at the zero x-axis at 0, and what I want at the from a model that is doing good transfer internally is improved quality on the low resource languages. And this improved quality is coming from the transfer from high resource languages. So if I train a single model in jointly with high resource and low resource languages, I'm expecting the positive language transfer happening from high resource to low resource languages. So the quality on the right-hand side here is expected to improve. And I make the model more, as I give more and more data, or more and more high resource languages are introduced, I expect this transfer to happen more and more for mid to low resource languages. So this is the first inductive bias. But here the sketch, the plot on the right-hand side is not that bright because you're not improving the data rich tasks, right? And our goal was to improve quality across the board for all languages. So how am I going to improve the data rich tasks? I'm just going to be scaling the neural networks up. And combined, as I make model more and more multilingual, and I make my model and I scale my model up and up. So this is the aimed quality, that's transfer and scaling, improved quality across the board for all languages, both on the left and right-hand side. Of course, the problem of expanding to new languages is still there. How am I going to be ingesting monolingual data plus parallel data simultaneously? And monolingual data is being ingested by the algorithms that are studied under unsupervised machine translation or unsupervised seek-to-seek models. But how am I going to confluence the supervised and unsupervised MT? That's actually a quite challenging problem, which we studied under the objectives. And at the end, I'll be given this data, I'll be given large models. How am I going to fit the model on the data? So this is the problem of learning or optimizing. This is the problem of optimization, and it's a huge problem in and of itself, because if you consider the imbalance in terms of the number of examples across tasks and the skew in the data sets. Think about the scenario: you're learning a model with the gradient descent, and you're sampling a batch of examples from this pool of data set. On some languages that you're going to be seeing a lot of data, on some you're not going to be seeing enough. So for the ones that you see a lot of data, you're going to keep learning. But for the ones that you don't see enough, so there will be not enough signal to learn. And if you try to balance this, then you can actually there's a chance that you can actually make it worse rather than better, because then you can start to overfit on the language that you don't have enough data, while you will be underfitting on the high resource languages. So this is actually quite challenging problem, optimization problem, because you have to control the learning signal. Yeah, so there are a bunch of inductive biases, bunch of bottlenecks that I'll be talking through. At the end, this seems like a quite compelling testbed for machine learning research. So if you think about the massive multilinguality that we're expecting the inductive bias of transfer kick in. So it's studied under multitask learning, meta learning, or recently under continual learning. And if you look at the massive scale, so that is mostly studied under model capacity. There are a bunch of areas that are working on trainability, optimization, and also generalization. But I didn't talk about, okay, I'll be training giant models, but will I be able to do it efficiently? That's also another research area. So it's actually quite compelling testbed for machine learning research. So the summary, this is the conclusion of my talk I'm going to be giving up front, which I notice I'm almost halfway there. But we have basically 4 takes out of the project. Multilinguality improves low resource languages. So here, what you're seeing on a dark blue line is a single massively multilingual model, and then compared against the 100 bilingual baselines on the x-axis at 0. So a single model is actually doing quite good, especially on the mid to low resource languages. So the first inductive bias check. And the second one is, as I scale my model more and more. So here you're seeing the red, a 6 billion parameter. In the green, you're seeing a 50 billion parameter model. So we're scaling the model up, and then you're seeing an improved quality across the board for all languages. So again, scaling improves overall translation quality. So the second inductive bias check. So this part I'm not going to be talking about too much in detail, but if you want to ingest a diverse set of data set, so we have to also mix different loss functions or objectives. So for the left-hand side, we're going to be using monolingual data with self-supervision and supervised data, so parallel data with supervised objectives. But on the right-hand side, as we go in the territory of unsupervised MT, we're going to be using a lot the different loss functions, which we devise, for example, cross-translation that enables indirect supervision, again, self-supervision that we use some masking loss in combination with online or offline back translation. And at the end, the model scaling has different effects on transfer capacity and trainability. So the scaling is not a silver bullet. So don't take me wrong. So I talked a lot about the scaling the models up and up, but scaling has different impacts on the transfer. So which I'm going to be sharing shortly. So it doesn't mean, so if I just blindfoldedly, if I scale my model, I shouldn't be expecting improved quality for all languages. The way that I scale is impacting the transfer, and also it's also generalization. And the particular way of scaling is quite important for my end goal. So I'll be talking about that too. Let's decompose the problem. So it's going to be easy. If I can decompose my entire machine learning problem as a function of f, I want to improve the quality. And I have this x, which is the data. I have the theta as the model, or like how I'm parameterizing. And I also bundle all the other loss functions optimizers and all the other governing hyperparameters under mu. But there is one more crucial component that's usually overlooked. It's the systems. How am I going to be orchestrating all these variables? How am I going to be training these models? What are the systems, infrastructures? How am I going to be enabling model and data parallelism? As I mentioned earlier, efficiency of these giant models are quite important. So these are the, this is pretty much the outline of the talk. So I'll be talking about the data first, modeling, and the training regimes the last. So this is the first. Let's start with the data. You can navigate yourself by looking at the top right. So just as a reminder, this is the training data that we had, I showed earlier. And we have the parallel data, like we trained single models for each one of these languages. This is how we came up with our bilingual baselines. So for every language pair, we trained a separate dedicated model to set our baseline. So we're going to be comparing our massively multilingual model against these baselines that are trained using the data available for one particular language pair. So if you look at the dark blue bars here, these are my baselines. And as you see, as the amount of data decreases, that I'm also seeing the drop in the quality. Just to remind you, this was the aimed quality. I was expected to improve the quality on the right-hand side. And let's see what's happening if I train a single massive multilingual model. I didn't mention one thing, the one detail. Since these models are, say, multi-way models, they can translate from any language to any language. So the evaluation is usually conducted from English to many or many languages to English. So I'm going to be measuring the quality of the model, for example, from English to French and from French to English. So when I'm going to be talking about many to one, I mean French to English or German to English or say Turkish to English. So the one here is always English. So you can also take it as many to English. And that's the quality on the left-hand side. But the other common evaluation practice is out of English or one to many. So that's where I evaluate my model on the directions originated from English to French, Spanish, and Turkish, and so on. So as you see, the left plot, I've shown that earlier, but actually you're seeing a problem on the right-hand side. The transfer is not that apparent when I'm translating out of English. Now think about you translating into multiple languages in an encoder-decoder architecture. So your decoder is now handling hundreds of languages. So this is, I talked about the transfer, but this problem that like all these tasks are competing with each other, or they start to hurt each other in a massively multitask environment, that is known as the interference. And interference is the source, or source of the problem that we're not seeing that much of transfer, which I'm going to be talking how we address the interference problem to improve the quality on the right-hand side of the plot.
Orhan, may I ask a question?
Sure.
So how come we don't have as much interference on the encoder side on the left graph?
Good question. So the target side is always English, right? So the amount of English data that I'm seeing in the decoder is actually a lot more compared to any other language that I'm seeing on the decoder. So the decoder is almost half of the time it's always seeing the English at the target side because of the construction of the data.
Right.
If you think about the data, since it's English centric, so the tasks are defined either into English or from English, right? So that's, if I don't control the amount of data that the decoder is seeing, then half of the time it's always going to be seeing English on the decoder. That's the amplification of the better English language model on the target side. So hence the quality is a lot better on the left-hand side of the plot.
So that you're still talking about the decoder though, right? So
that's correct, yes.
You know, what I was wondering is why a similar argument doesn't apply to the encoder side, but
I see. So there, yeah, okay, I see the problem. So in these models, since these are sequence models, we are not decoupling the inference problem. So we are fitting on the model, but we are not decoupling. So we are fitting on the problem, fitting on the data during training, but at inference, we are applying a technique that is a heuristic, say beam search. Mm-hmm. And search seems to be a lot difficult in a multilingual decoder because the search space is becoming a lot, say, complex, or the search space is becoming a lot larger because now I'm not only trying to decode in one language, but I'm trying to first decipher, okay, what was the language that I was decoding? And then in that language, what was the vocabulary that I was trying to narrow down the search space? So the search problem is becoming a lot harder in multilingual decoders. So that is one source of the issue. Decoupling the impact of encoder and decoder is not well studied because of this inference problem is not, to my understanding or to my knowledge, this inference problem is not easy to control. So that's my take.
So in the massively multilingual model, so we have multiple languages incoming, multiple languages possibly outgoing.
Yes.
In terms of architecture, for example, is it a single decoder that generates both English and Turkish and French, or is there sort of a branching inside the model into these different language decoders?
This model is a monolithic model that everything is shared. So both encoder, decoder, so the entire parameter space is shared across all languages.
In which case, how do you control what language is output?
You're giving a tag, or you're giving a bias vector, or you're indicating the decoder or encoder, okay, this is the language that I want to decode into.
Okay.
By giving either a one-hot vector, or you're prepending your source sequence translate into German, English, etc. in the source side or the target side.
Thank you.
All right, but let's remember the full spectrum of the available data. I only talked about the picture on the left-hand side when we were using the supervised data that was on blue. But of course, how am I gonna, and then we showed supervised multilingual MT was actually enabling the positive language transfer, where the the high resource languages are benefiting the low resource pairs to improve quality. But of course, how am I going to be improving the quality on all these unsupervised languages? That's an open problem, which I'm not going to be talking about, but we have some ongoing work. So if you're interested on that part, I added a couple of links here. Please feel free to take a look. So I'll be going into the modeling section. So this is the part actually that I'll be answering a lot of questions that I just got. So the architecture that we're using, or the particular wiring that we're using, is called encoder-decoder architecture. And the parameterization is done by using the transformers. So we're basically using, in the baselines, we're using vanilla transformers with a few tweaks, but they're not that important, so we can ignore the details. But in a vanilla transformer, encoder-decoder, we have an encoder stack that inputs that ingests or that encodes the input sequence, and I have a decoder stack that generates an output sequence given the input encodings. And it's built by using self-attention and cross-attention layers cascaded. In terms of the parameter sharing, so there are different approaches on the parameter sharing. So we can share nothing, that's on the left-hand side. I can just share a fixed length vector across all languages. But as you can imagine, this creates quite some bottleneck. I can share some small modules, and then I can leave, say, encoders or decoders language specific. But as you can imagine, this increase, that's in the middle part. But that, as you can imagine, this is increasing the number of parameters as I add more and more languages. And on the right-hand side, I can share everything. So that is actually quite parameter efficient. But this monolithic architecture is creating a lot of, it's enabling transfer, but it's also harboring a lot of problems because of it's the source of interference. You allow tasks to benefit from each other, but also you allow them to compete for the capacity if they have a lot of data. So there is a tug of war between transfer and interference there if you use the right-hand side. But let's start with a model that's on the right-hand side. So this is the model that if you use the monolithic model that you share everything. But again, so the premise was I'm going to be increasing the scale of the models to boost the quality on the high resource languages. So how am I going to do it? And as the field, where are we now? I mentioned, so we are scaling the neural networks up. So we are seeing all the neural nets these days. They're large. They're trained on very large amounts of data on hundreds of languages and tasks. But the observation here is they actually generalize quite well. So this is challenging the classical bias variance dilemma, where as I make my model more complex, I'm not actually overfitting. I'm actually generalizing better. There's also another debate these days. So are we getting close to human? Are we bridging the gap with human parity? But I'm not going to be going into the detail of that. Also, why do large neural nets generalize better? Basically predict well on the unseen data. There is some actually theory behind this that's connecting that's connected to over-parameterization and how is it tied to optimization and so on. So I'm again not going to be going to the details of this, but at the end, if we decompose learning, we end up with two terms: so optimization error and statistical error. We also call the latter estimation error, but basically generalization. And these two do not interact in the classical machine learning. But in the modern neural nets, these two areas are intertwined, making the problem a lot more complicated to study. So according to some studies, the over-parameterization is also playing a huge role in this picture, and it's actually connecting the whole thing into deep double descent, or it's the new look on the classical bias variance dilemma. So there's a huge literature. This is an ongoing research topic, actually, like all deep learning theories now investigating this. But I wanted to mention that, of course, generalization goes beyond optimization and statistics. It touches the causality, compositionality, and more. But these are kind of like beyond the scope. So I'm going to be focusing on how are we scaling more. So like when someone says, okay, I'm going to be scaling these models, the first thing we look at, okay, are you going to be making these models deep or wide? So which one is actually allowing you to attain better quality, and how deep that you should go, and what are the efficiency trade-offs while you're going deep or wide? Or are there any other techniques that you can scale the models up? So here we did a controlled experiment. We kept the number of parameters for a massively multilingual model at around 1.3 billion parameters. And we scaled it in two different axes. Either we scaled the model by making it wide, that corresponds to the orange curve here, or we made it really deep, but we always control the number of parameters, and we kept that 1.3 billion. Of course, we can debate whether we should be counting the number of parameters when we're talking about the expressivity of a model, but again, that's kind of beyond the scope. But here what we are seeing, if we control the number of parameters and if we just change the depth or width, we're seeing a different transfer dynamic, right? So here the orange one is a wide model and the dark blue one is a deep model. And we're seeing deep model is actually doing better on the low resource end while they're performing equally well on the high resource languages. So if generalization is, like if positive language transfer is an indicator of generalization, then I can say deeper models do generalize better. And if they're generalizing better, why I'm not actually pushing it to its extreme? So we actually pushed it further. We trained even deeper model, and we observed as we make the models deep, they generalize better. But I should note the model here that we trained that has almost 128 layers. That took us 5 weeks to train. So and we were using 2,000 chips. So that corresponds to almost 4,000 GPUs. And it was quite expensive and painfully slow.
Orhan, can I ask a question? So yeah. in this last graph, you gave up on keeping the number of parameters constant, I assume, right? So the parameters are actually growing.
Yes.
So in vision, like efficient net and stuff, people are sort of finding that proportionally growing the width and depth might actually be better instead of just doing one or the other.
Proportionally in the sense that proportional to.
So basically, are you familiar with efficient net at all? So
yeah.
So they calculate some coefficients. And between the 0th order efficient net and 7th order efficient net, they basically multiply both depth and width with some factors, and they basically find out what the ideal factors should be by experimentation. So
I see.
Here you're only doing one or the other. I'm wondering if both would be interesting. And then the other thing I was wondering is the third thing that vision people do when they're growing their models is play with resolution. So in vision, you can take an image and you can play with its input resolution. In language, there is nothing quite corresponding to that, but maybe type of tokenization used or the vocabulary size might be something similar. So that's another dimension that you experimented with. So I'm wondering if you have any observations on either growing things proportionally or playing with tokenization.
We have tokenization is affecting the vocabulary size and also the segmentation ratio. At the end, it yields a different sequence length. But in the asymptote, we haven't seen that much of a difference. So these models are almost all character-based models, by the way, because they have hundreds of languages with a limited vocabulary size. So they end up all with a vocabulary, it's a character-based model. So we're not seeing that much of a difference across different type of models because they all characters, but we are seeing some difference in terms of like there are different governing scaling laws as you increase the sequence length or you go beyond the sentences. So yes, we are seeing some difference, not because of the vocabulary or like the tokenization, but we're seeing some difference as we go beyond the sentences.
I see.
So like all the results that I shared, they're at sentence level, but now we're actually working on document level or the larger context. There we're seeing different patterns, yes. And in terms of scaling encoder and decoder, so there is this natural separation of roles in the encoder-decoder architecture. So we have this assumption or this intuition, encoder is more of a feature extractor, and then decoder is more of a generator or sequence generator. Right. So they're actually playing a different role. And depending on the multilinguality or how many tasks that you have, the scaling encoder helps, for example, if you are aiming to increase the coverage on the source side, but the decoder depth starts to make a lot of sense, or it becomes important if you're translating it to multiple languages, or if you want to generate more natural looking text. So you can still use a shallow encoder, but as you make your decoder deeper and deeper, as much as you can afford, so it tends to generate more natural text. So that becomes at some point almost indistinguishable from natural human generated text. But these are mostly all bound by the infrastructure limits. So I mentioned here this 128 layer GPipe. So to be able to train this, this was at the limit of the hardware boundary. So we had to develop GPipe to be able to go 128 layers first. So if you look at what is the scaling law suggests, it's suggesting us to scale even further than these numbers, but that's not the limit, that's not within the limits of our hardware or our tricks that we use at optimization.
So what you said about scaling the encoder and decoder is interesting because we were looking at sort of the other extreme of how little computation you can use to get by with one language, and we found that actually downsizing the decoder has less impact on BLEU score versus the encoder if you're just talking about a single language pair. So you can get rid of a lot of the decoder without losing much quality in that case.
Yeah, we have the same observation, but that breaks if you have a lot of languages in the decoder.
Right.
So there you need capacity and depth. Yeah, but yeah, like observation, we have the same observation on single language pairs. Yes.
Thank you.
Right, I'll speed up a little bit. So over the last couple of years, we're seeing an increased trend on the model sizes. So this is basically here what you're seeing on red. These are the M4 models. But the take here is the models being built in the field scaled by 3 orders of magnitude in only 2 years. And we also see a constant improvement in the end quality. So this is remarkable. That's also, this ties back to the initial comment that I made. The scaling is predictably increasing the generalization. So what's in it for me if you're asking, if you have 2 GPUs and if you're training 2 models in isolation on these 2 GPUs, maybe it's a good time to consider training a single but larger model distributed on 2 GPUs rather than training 2 smaller models. So let's look at the scaling paths I talked about, going either deeper or wider, but they're all under the dense scaling part. So either I'm increasing the depth or width, and in these densely scaled models, every input actuates the entire network. So you're basically touching the entire network as you compute or as you process. And some examples are GPT-3, T5, and the previous GPipe-based M4 examples that I showed, they're all densely scaled models. But these models have a lot of bottlenecks. The optimization is a big problem. gradient flow in the oboe, like a gradient flow in the forward passes is in the backward pass is tricky. Initialization, as you go deeper, it becomes really tricky. And also they're very long that takes a very long time to train these models. But on the other hand, we also have sparse models that you route the processing. So every token does not touch the entire network, but you conditionally route the computation. So this is studied under conditional computation, where the only part of the network is activated depending on the difficulty or depending on the type of the input. So these are the type of models that we study under sparse scaling. So how does this look? A densely scaled model, it looks like, so I have here 2 data points that are coming from task A and task B. This is a token level processing. So I have only a single token, one in Chinese, the other one is in English. And I have a stack of layers, and dense scaling is basically you process every token by every layer of the network. So this is quite time consuming. Now imagine that you're increasing depth or width. So it's proportionally increasing the processing time. But in a sparsely activated model, the processing is a little bit different. So here I have again the common blocks. These are the layer 1, layer 3, and they're actually the common blocks that I showed in the previous one. But I also have some expert layers, or the layers that I make the routing decisions, or I route the processing. Here in these expert layers, I have expert modules. These are simple, like, just a second. Okay, sorry about that. So here the expert modules are single feed-forward layers and so on. When how my processing in an expert layer is, or in a sparsely activated model is. So I'll have these router networks, these sub networks that decide, okay, this token should go to that expert, that token should go to the other expert. And then I have a combining network that combines, basically takes the weighted average of all these and then keeps processing. So this is, if you look at the expert layer number 2, there are actually inactivated experts. And if you can imagine, I increase the capacity by adding a lot of experts. So majority of the experts are not going to be activated. So not every example or not every token will be activating the entire network. So I'll be actually making it a lot more efficient to train these models. And the rest is pretty much the same. So this is what we call the mixture of expert transformers and how it's actualized. So we basically replaced every other feed-forward layer with an expert layer. So this expert layer here that you see is the one that I introduced previously. It has a lot of feed-forward layers as the experts, nothing fancy, and distributed. We place the entire transformer body on different devices. And then replicate the entire network. But we are not replicating the experts. So we are basically, so now here, like in this example, I have 2 chips or 2 devices, and I'm going to be having a replica of the entire network, but I'll be having only a single copy of the expert number 1 on the chip 1, and a single copy of the expert 2 on the chip 2. So this allows you to not exchange any gradients for the experts. And the only communication is in the gating decision. So the model decides, okay, this token should go to that expert, and then it just routes to that expert. And then you don't even need to exchange the gradients for the expert layers because everything is local. And if you think about, if you increase the number of experts, so it's here, the example is given on only two experts. But if you think about, you have 2,000 or 4,000 experts, so this is becoming actually quite efficient. So you're increasing the number of parameters dramatically, but you're not actually scaling super linearly. Actually, it's a sublinear scaling. And in terms of the quality, so these are the quality results. So here, let's look at so here we're gradually scaling the models up. And on the top there, you're seeing a model on the blue, you're seeing a model that's 36 layer deep. It has 2000 experts and it has in total 600 billion parameters. And it's like as you go down, it gradually decreases the number of parameters, and at the end, it meets the slight the solid solid black line. That is the best previous model that was scaled in a dense manner that I showed earlier. That was taking 5 weeks to train using the same number of chips, but this sparsely scaled model that is on blue, that took us 4 days to train using the same number of chips. So the sparse scaling is not only almost 10 times more efficient, it's also, it yields better quality all across the board. Again, scaling has different effects on or it has different impact on the transfer dynamics. 600 billion parameter is good, but it's actually not good for all the languages. So there's an inflection point there where we see actually 150 billion parameter model is actually doing better on the low resource languages. So if you think about it, 150 billion parameter model, it has 500 experts. So the less number of experts that you have, the more parameters that you share. The more parameters that you share, the better transfer that you observe. And the better transfer that you have, more interference on the high resource languages, but actually the better transfer on the low resource. So there's different transfer dynamics as you scale the models up. So that's the point that I wanted to make in terms of the scaling. So the take here is the dense scaling is good, it's straightforward, but the scaling is super linear. So as you scale more, it's gonna get slower and slower. But sparse scaling, it minds the computation and communication requirements, and each token only activates a subnetwork, and the scaling is sublinear in this case. So it's a lot more efficient, both compute efficient, and it's also delivering better transfer dynamics. And you iterate actually faster, so you can come up with a better architecture that is better optimized. So what is next? There are different routes. So there's several, if you're interested in this area, so there are actually several open problems that are touching on the routing decision, how the routing should be made. And these actually are studied in a very, very small scale. So not all these experiments are, so when you're studying the routing, you're not actually studying this at scale, we're studying at a very small scale. So please do not get intimidated by the scale if you want to study the routing or sparse models. This is a very active topic, and I encourage everyone to take a look at the sparse scaling methods or conditional computation in general, where you make the decision inside the network based on some criteria that is learned or that is given. But there's a lot of room for improvement for sparse models and also conditional computation. I was planning to talk about another type of sparse model, which is we call task MOE, but I'm going to be skipping that one for the interest of time. And I'll jump into training regimes and optimization.
Can I ask a quick question?
Sure.
Before you move on. You showed us results from networks with different parameter choices, and the plots are from your final models. I'm just curious to see if the relative rankings and the eventual learning abilities of these models are evident in the earlier stages of the training, and if it's at all possible to kind of figure out which model will yield better results without having to all the way train it.
It's a great question, and the answer is yes. But there's a caveat. So we observed there are some phase transitions at the early stages of the training. So we have this different that touches the optimization actually. The next part, the particular way we train or particular way, the approach that we use in the optimization, it's using a handcrafted learning rate schedule. And at the beginning of the training or the optimization, you're using a warm-up state. So this warm-up stage is acting as a stabilizer if your initialization is not good. So within the warm-up phase, everything is quite chaotic. So you cannot predict anything. But after the warm-up is done, after that initial burn-in phase, then things become more predictable. So then this diffusion, dispersion, there are some connections with that. But if you can wait until the warm-up is done, then from that point on, the scaling becomes more predictable, or the loss that you're going to be getting at the end, it becomes more predictable. But I should also note the larger models they're more, say, brittle. So they're more sensitive to outlier examples. So it doesn't mean that the model will definitely converge. The model may actually blow up if it sees a malicious example. And that malicious example, that outlier, may not be a triggering example for a small model, because it might have already smoothed out its distribution, so it might not be affected too much by that example. But the larger models, they become more confident in their decisions. So when they see outlier examples, they yield higher, say, learning signals. So it's like what I mean, you're seeing either an exploded actuation in the forward pass or an exploded gradient in the backward pass. So yes, in short, after the initial burn-in phase, you can predict which model is going to be doing better, but you should also account in the outliers or some malicious examples.
Okay, thank you.
Right, I'll talk about the training regimes and optimization. So I actually misled you at the previous plots. So when we trained massively multilingual models on the available data, by using the original data, this was actually the plot that we were seeing. So if you remember, we were using this billions of data on the left-hand side and a handful of data on the right-hand side on the supervised regime. So if you use the data as is, and if you just sample, if you use the SG, the stochastic gradient descent, and just sample a batch from that data, this is the plot that you would see. So what we did actually that I didn't show, we were balancing the data across different language pairs. And this is the part that I just wanted to show the importance of what happens if you don't balance the amount of data across different tasks. So you're not seeing any transfer both on the left-hand side or the right-hand side. So actually, if you mess up at the optimization or scheduling, data scheduling, so there is no guarantee that you're going to be seeing any improvement. But how am I going to be sampling a batch, forming a batch, and update under this imbalanced environment? I can just look at the data. That's a sampling heuristic that I mentioned earlier, and it's actually working quite well. Or I can learn to sample. There's a huge area on this, how to sample, how to pick up one task, and so on. Mostly studied under bandit-based algorithms. Or I can look at the model itself. What does the model think about the current progress, or how much the model think? What does the model think? How much benefit that it can get out of a sample batch? And we can look at some model internals. We can look at the gradient, evaluate it on a held out set, and then we can check whether it's aligning well with what the model thinks. Or we can change the learning rate for different tasks based on the progress on a particular task. If it is moving too fast, we can slow it down for that task, or we can speed it up for other tasks. Or we can, of course, look at both. So I'm going to be talking one example here. So by the way, just how we balance the balancing heuristic. We use the temperature-based heuristic. That's quite common. That's being used by Ember T5. So I'm not going to be talking about, but this is the first method. That's basically a heuristic. And if you use this heuristic, a temperature-based scheduling, that'll give you the green curve here. That was the plot that I showed earlier. But if you look at the gradient similarities, that's actually speaking a lot more. That's telling you a lot more. So here, what we did was we looked at the gradient similarities across different languages in this massively multilingual model. And what we noticed here, the x-axis and y-axis, they're clustered with respect to the linguistic similarity. What we noticed in aggregate, if the languages are linguistically similar, that they also yield similar gradients. So there is actually an indicator. So like the assumption or the intuition, okay, similar languages should help each other. We were also able to see that in their gradient similarity. So the more the similar their gradients, the better the optimization gets. So the more that they help each other. And we actually looked at this even further, but we separated out two directions. If you remember, when we're translating into many to English or X to English, we were seeing a better quality in the better end quality. But we were not seeing the same in when we were translating from English to X. So this is actually ties back to the question that I got earlier, why we were seeing better quality into English, but not into other languages. We noticed when we're translating into English, the gradient similarities across different languages is a lot higher. So here, the single cell is the gradient similarity between Spanish and French. And it's almost like the correlation is super high. It's almost 1. But on the other hand, also we are observing improved quality. We are seeing a lot better transfer dynamics when we're translating into English, right? So we were also able to see that in the gradient similarities. But the situation is not that good when we're looking at the other direction. This is the right-hand side. Gradients do not correlate well, and as they do not correlate well, the quality also drops. We actually measured this. We picked up 2 languages, and we looked at, okay, we trained 2 language model, a multilingual model on 2 languages only, and we looked at their gradient similarity. And we noticed as the gradient similarity increased, the blue score also increases. So this is also another evidence. The gradient similarities is telling us something in terms of the transfer dynamics of the model. So the better the gradients align, the better transfer that we observe, the less interference that we observe. So given these 2 observations, what we can do about the optimization? So we devised this algorithm that we call gradient vaccine, that we try to ensure tasks have always positive gradient similarity over the course of training. So what we do here, we pick up a language, we pick up a task that we know that is representative of a linguistic family or that is high resource. So that's given in blue. And we set a similarity goal. So it's basically an angle, it's a hyperparameter, it's the similarity goal. And so what we try to do, we alter the gradients, we alter the gradient of the auxiliary task or the task or the low resource language to align with the gradient of the primary task. And we just basically alter both the magnitude and the direction of the gradient of the other task to align with the primary task. And every update, we do this, the preemptive, say, surgical thing, or that's why we call this gradient vaccine. We apply this change and then carry out the optimization. And we noticed, so that is the example. So that's the gradient vaccine given in green. So we observed improved quality, especially when you're translating out of English. So that's given on the right-hand side. So it's mitigating the interference. It's allowing it's mitigating the interference, and we're seeing that on the high resource languages, they don't interfere with each other. They don't interfere with each other as much as they used to. So that was the gradient vaccine. So it's actually a very simple trick that we incorporate during training. It's still using a lot of, say, prior knowledge. Okay, what should be the primary task, or what should be the gradient alignment objective? So how much they should align, because they still determine the end quality. But it was a simple approach that is showing the impact of how gradients or gradient similarity impact the end quality in a multitask learning environment. So that is,
ask a quick question?
Sure.
So at the beginning of your talk, you have mentioned these inductive biases. And like you show us here, we have also some inductive biases about the languages as well. Like these two languages are similar to each other.
Yeah.
We basically have a family of languages, but in a way, in this particular manner, you are not using this explicitly, but in a more implicit manner. I was just curious about, like, for example, maybe for low resource languages, sticking to a curriculum learning strategy might also help the performance on those low resource languages. So
I see. So this is some sort of a curriculum implicitly implemented. So the curriculum here is for your low resource task, just try to align its gradient, just piggyback on the learning process of a high resource language. So just use the representations that you think that is the most similar to yours, and then just don't disagree with that one, just agree with that, and then try to be opportunistic and then use the representations around that region. Say that's why the gradients are going to be moving in that direction in the parameter space. So that's kind of like an implicit curriculum, but of course the prior or the inductive bias that we're using. So what is the auxiliary task and what is the primary task, and how much that we should what is the angle here, the agreement angle, right? The targeted angle, what should that be? Because that also determines this exploitation and exploration, right? So if you set it too narrow, then you're not going to be exploring for the low resource language. So you're only going to be exploiting the high resource benefit. So that's okay, but yeah, there's actually a trade-off. So we haven't delved too much into that. But that said, the curriculum learning, I think that's also another area which has, I think, less priors than the one that we have here. But yeah, to answer, yes, we're using some implicit curriculum assumptions, but not fully.
Thank you.
All right, that was actually the end of my talk. What did we cover? So we covered only 3 different aspects of the entire problem: the data, modeling, and training. But there are several other issues. The generalization I mentioned earlier, the premise or the goal is generalizing across languages, register styles, but the generalization is also tied to evaluation. And evaluation is quite tricky in natural language generation. And I think I can say we're in the evaluation crisis right now in the NLP community. So that's a big of a problem, probably can be a talk in and of itself. Data sets are quite problematic. I didn't talk about how we found the additional 400 languages, but that was a quite rocky path. So crawling from the web, not all languages that you think that they're that language. So they might be a language that's written in a different script that's just fooling you. The noise in the data set is a big determiner. I briefly talked about the inference, but I didn't talk about how are we serving these models. I should have told at the beginning, but whenever you use Google Translate or any other product, actually you use the model what I have already presented. So these models are already in, say, production, but I didn't talk how we made them into production, because these are giant models. How we made them more inference or serving friendly, I didn't talk about that. Again, I briefly mentioned beyond sentence level, what's the behavior on the document level or larger context. Again, I didn't talk about much. Vocabulary, I briefly touched. Vocabulary is actually affecting a lot, and we're actually moving more and more to byte level or even bit level processing. And we are also observing a merger between vision and language. I didn't talk about that too. Systems part, I briefly mentioned G-pipe or G-shard, but there's a huge space or huge research going on there on the systems part. And also, if you're not actually interested in machine translation, but if I'll give you this model, that is pre-trained. What's in it for me if my task is, for example, I want to test this on XNLI, what's their capability on cross-lingual downstream transfer. There are actually some signals that these models are doing good on that too, but I also didn't talk about for the interest of time. I noticed that I'm significantly over time. So thanks everyone for listening, for your patience and attention, and sorry about the initial hiccup at the beginning. That happens sometimes. Thanks everyone.
Mm-hmm. Thank you, Orhan. Actually, we got some questions during your talk, but maybe we can take maybe one or two short questions. Yeah, Kerem?
I wonder that such a deep model, did you observe something like that? Some layers specialized in low resource language and some layers are specialized in normal language, or any specialization across different families of language. Also, I wonder this situation, especially on expert layers, and did you carry out any probing experiments for those layers?
I see. We didn't carry out any probing. So let me we didn't carry out any probing experiments. But in terms of the specialization, I wish we the final say is it depends from model to model. So what you're seeing in one model may not be the same for the other model. Even if they have the same architecture, if you change the initialization, the optimization schedule, you're seeing a different trend. So in some models, the bottom layers seem to be doing a lot more for the low resource, but in some other model that's using the same architecture, but a different initialization, that seems to be doing different. That has a different, say, distribution of the computation. There is a trend that lower layers are more sensitive to syntax, and higher layers are more sensitive to semantics. We have some evidence, but I'm not that confident to conclude that that's true across the board. For the sparse models, what we are seeing is the expert specialization is definitely happening. Expert specialization, but it also depends on the type of the sparsity that you're using. I presented the token level experts. So their tokens are shared. So what I mean by a token, it's basically a word or a subword, and some subwords are shared across different languages. So we noticed, for example, some experts are specializing for some common subwords that are shared across different languages, that shared across many languages. Some experts are specialized at punctuations. Some experts are specialized at say named entities. But that also changes so there's not you can find out these experts, but you have to redo the thing for a different model that if you start from scratch. So every model is, although their end quality is the same, they learn a different representation at the end of the day. So yes, there is some sort of specialization happening, but I don't think they do generalize across models.
Thank you.
Okay, I think we can thank our speaker. Thank you, Orhan, for giving this really interesting talk. Yeah.
Thanks everyone for listening.